So now we are going to study about the hyperfine interactions of the Mossbauer spectroscopy. So out of this we are going to study about the isomer shift and magnetic hyperfine interactions. So first of all we are going to learn about isomer shift. So we know that in a Mossbauer experiment we have a source and the absorber. Source is a crystal that contains the excited nuclei of the given isotope, and the absorber is another crystal containing the same isotope which is in the ground state. So the source will emit the gamma radiation and the absorber will absorb the gamma radiation. But if the environment of the source and the absorber are different, the energy of the nuclear transition E0 may differ by a small amount. So this energy difference is known as isomer shift delta or chemical shift. So the term isomer shift is generally used because the effect depends on the energy difference between the ground and the excited or isomeric state. So the effect of the isomer shift is to shift the resonance line from the zero position. The isomer shift delta can be either positive or negative depending on the sample. The isomer shift arises because the nucleus of the atom is not a point charge as assumed, but it has got a finite charge distribution. So the nucleus is not a point charge, but it has got a finite charge distribution. So because of this, there will be an isomer shift. So the electrostatic interaction between the nuclear charge distribution and the electron charge distribution will cause a change in the energy levels of the nucleus. So the shift in the energy levels of the nucleus due to this isomer shift is given by delta E is equal to 2 pi by 5 Z E square R square modulus I 0 square. The modulus I 0 square is the total electron density at the site of the nucleus, and Z is the atomic number, E is the charge, and R is the effective radius. So every level will be changed by an amount of delta E. So the ground state will change by an amount delta E ground state, and the excited state is changed by an amount delta E excited state. So this is the ground and excited state of the source, and this is that of the absorber. So each level is changed by an amount delta E, and delta E is different for ground state and excited state because R is different for the ground state and the excited state, and it will be different for the source and also for the absorber. So we would like to find the energy difference, change in the energy difference between the nuclear, ground and excited levels. So the change in delta E between the excited and the ground states are given by 2 pi by 5 Z square mod psi 0 square whole multiplied by R square excited minus R square ground. These are not equal. R square excited is not equal to R square ground, so that this term is not zero. So the energy difference between these two levels can be written as ES is equal to E0S, the energy difference without considering isomer shift, plus delta of delta E, where R is the radius of the equivalent sphere of uniform charge distribution, and R can be taken as the average of the radius of the excited state and that of the ground state, and dr is the difference between the radius, equivalent radius of the excited state and that of the ground state. So R square excited minus R square ground can be written as this is a square minus b square, that can be written as a plus b into a minus b. So This is of the form of a square minus b square. So this can be written as r square ex minus r square ground is equal to r square ex plus r square ground multiplied by rex plus rgr multiplied by rex minus rgr. So this can be written as 2r and this is dr, 2r dr, and multiplying both the numerator and denominator by r, we will get 2r square into dr by r. So in the Mossbauer experiment, we measure the difference in the nuclear electrostatic energy states of the source and the absorber. So this is for only one kind of the species, either for the source or for the absorber. So we have to find the difference in energy levels for the source and the absorber, so which is represented as isomer shift. And isomer shift is represented by delta, which is delta of delta E absorber minus delta of delta E of the source. So which can be written as 4 pi, substituting these values over here for the above equation, we will get 4 pi by 5 Z square r square dr by r modulus psi 0 square of the absorber minus modulus psi 0 square of the source. So where the psi 0 square comes from mainly, this term comes from mainly from the s orbital, that is psi 0 square is the electron density at the nucleus. So this is non-zero only for s orbitals, as we have seen in the case of ESR also. So this other orbitals P, D, F, they are having a node at the nucleus, so their psi 0 square term will be 0, but they have an indirect interaction by the way of shielding the outer s electrons. For example, 3d5 4s1 has got a larger value of psi 0 square than 3d6 4s1, because this extra d electron here shield the s electrons from the nucleus. So this has got a larger psi 0 square value. So even though the psi 0 square value of P, D and F orbitals are zeros, they will have an indirect interaction by shielding the outer s electrons. More number of if we have more number of P, D and F orbital, the shielding will be more, and this term psi 0 square will decrease. So as we have seen in the above equation, the isomer shift depends on these quantities, that is isomer shift is equal to 4 pi by 5 Z square r square dr by r multiplied by psi 0 square of the absorber minus psi 0 square of the source, and this term is called the nuclear term and this term is called the chemical term. So r square into dr by r is called the nuclear term, which is constant for a given Mossbauer transition, and this term psi 0 square of the absorber minus psi 0 square of the source is called the chemical term. So the chemical term represents the difference in the total electron densities at the absorber and the source nuclei. So and therefore for a given transition, this is a constant, so delta depends only on this, and therefore the isomer shift is sometimes referred as chemical isomer shift. So if this quantity dr by r is positive, then delta is also positive provided psi 0 square of the absorber is greater than the psi 0 square of the source. So mainly this dr by r term and the chemical term psi 0 square of the absorber minus psi 0 square of the source determines whether the chemical shift delta is positive or negative. So we can explain this with the help of an example. For example, iodine 127 and iodine 129 resonance of Na3H2IO6. So here the source used is the zinc telluride containing tellurium 127 and tellurium 129. So this is the source for this. So this isotopes, the zinc telluride isotopes, undergo beta decay and emit gamma radiations, and this Na3H2IO6 act as the absorber. So there are two isotopes, one containing iodine 127 and another containing iodine 129. So in the case where the iodine 127 is there, dr by r is negative. But for iodine 129, dr by r is positive. But for both cases, the psi 0 square of the source is greater than the psi 0 square of the absorber. So, the psi 0 square absorber minus psi 0 square source is negative for both cases, and therefore delta for iodine 127 is negative into negative, is positive. And for 129 it is positive into negative. So if we are using two isotopes here, so one has got a positive delta which contains iodine 127 and other has got a negative delta which is iodine 129. So if we plot the corresponding Mossbauer spectrum, we can see that, and sources source here is zinc telluride containing tellurium 129 and Na3H2IO6 containing iodine 129. So in this case delta is negative. So we can see the absorption, maximum absorption at this point, which is shifted from the zero position towards the negative velocity region. So negative relative velocity region. So in this case delta is negative. So actually we expect the shift absorption to be maximum at the zero position, but here we are getting the absorption maximum here at this point. So it has which is shifted towards the negative region. So it has got a negative delta. For the other source which containing iodine 127 as the absorber and which contains tellurium 127 as the source, we can see that the delta is positive and the shift occurs here. So the absorption occurs at this point, shifted towards the positive region. So the resonance of iodine 127 occurs on the positive side and that of the iodine 129 occurs on the negative side. The next hyperfine interaction of the Mossbauer spectroscopy is the magnetic hyperfine interaction. So most of the Mossbauer nuclei have a non-zero value of the spin on the ground state and also for the excited state. So I not equal to 0 for the ground state and also for the excited state. So we know that in a magnetic field every level split into 2i plus 1 levels depending on the mi value. So we know that the mi can take values from minus I to plus I. There are 2i plus 1 possible values of mi. So the interaction energy of the nucleus in the magnetic field is given by EMI is equal to minus Gn mu n b into Mi, where mu n is the nuclear magneton. It's a constant for a particular nucleus, and Gn is the nuclear G factor, and B is the applied magnetic field, Mi is the magnetic quantum number of the nucleus spin. So the magnetic field split. So in the presence of the magnetic field, the ground state split into 2i plus 1 levels, and the excited state also split into 2i plus 1 non-degenerate equally spaced levels. So we can consider a specific example. For example, the ground state has a nuclear spin of half. So let us represent by the ground state by double prime. So Ig double prime is equal to half. And the first excited state has a nuclear spin of 3 by 2. So we can represent the excited state by single prime. So IE prime is equal to 3. So we know that every level split into 2i plus 1 levels. So for the ground state, I is equal to half. So that split into 2 into half plus 1, 2 levels. And the excited state, I is equal to 3 by 2, and it splits into 2 into 3 by 2 plus 1, 4 levels. And the energy of each level is given by EMI is equal to minus Gn mu n B mi. So we have seen this already. So for the ground state, we will find the energy levels E half. So putting Mi is equal to half over here. We will get minus is already here. Minus half into G n double prime. So as this represent the ground state. So the ground state is represented by double prime, and the excited state is represented by single primes. So minus half into Gn double prime mu n into B. And E minus half, minus will be positive over here. Half into Gn double prime mu n B. So here we have taken this Gn double prime. Gn double prime is the nuclear G factor of the ground state. Gn double prime, and Gn prime is the nuclear G factor of the excited state. So we assume that both the Gn prime and Gn double prime are positive. So E minus half is positive. So E minus half has got a greater energy than E plus half. So we have this Mi is equal to plus half has got a lower energy, and Di is equal to minus half has got a higher energy. And now for the excited state. So for the excited state, we can have 4 Mi values. I is 3 by 2. So Mi can take values minus 3 by 2, minus 1 by 2, 1 by 2 and 3 by 2. So writing the expression for energy for each case, we can see that E minus 3 by 2 is 3 by 2 Gn prime mu n B, where Gn prime is the nuclear G factor of the excited state. So since Mi is negative, and already we have a negative over here, this value is positive. So E minus half is half into Gn prime mu n B, and E plus half is minus half into Gn prime mu n B, because Mi is positive but there is a negative over here, the product is negative. So E 3 by 2 is minus 3 by 2 Gn prime mu n B. So out of this we can see that this is having the maximum energy. So minus 3 by 2 has got the maximum energy. Next energy is minus half, then plus half, then plus 3 by 2. So these are the energy levels of the excited state, and these are the energy levels of the ground state, provided the nuclear G factors are positive. So now the selection rules of these transitions are given by delta Mi is equal to, so delta Mi is equal to 0 plus or minus 1. So from plus half, there are 3 transitions are allowed: plus half to plus 3 by 2, plus half to plus half, and plus half to minus half. And from minus half to plus half, minus half to minus half, and minus half to minus 3 by 2. And a total of 6 transitions are allowed. Here and we get 6 lines. So the energy of these lines can be found by subtracting the energy of this lower level from that of the upper level. So the energies of the 6 lines are given by, one is half into mu n b 3gn prime minus gn double prime, half into mu n b gn prime minus gn double prime, minus half into mu n b gn prime plus gn double prime, half into mu n by gn prime plus gn double prime, minus half into mu n b gn prime minus gn double prime, minus half into mu n b 3gn prime minus gn double prime. So we can calculate this from the corresponding energy levels. So for a particular transition, if we subtract the higher energy state, if we subtract the lower energy state from the higher energy state, we will get this the energies of the lines. Now we can discuss specific examples. So for example, in tin 119, Gn double prime is negative and Gn prime is positive. Then what will happen? So that Gn double prime means the nuclear G factor of the ground state. So if it is negative, there is an inversion of levels in the ground state. So in the example, we have seen that E minus half is having a greater energy than E plus half for the ground state. But if Gn double prime is negative, E plus half is having a greater energy than E minus half. So now another example is iron 57. Gn double prime is equal to 0.1804 and Gn prime is minus 0.1027. So this is negative. So that is the nuclear G factor of the excited state is negative. So in the energy level scheme of the ion 57, there will be an inversion of levels in the, that means in the excited state of the ion 57, minus 3 by 2, Mi is equal to minus 3 by 2 has got minimum energy because Gn prime is negative, and Mi is equal to plus 3 by 2 will have maximum energy. So if we see the Mossbauer spectrum of iron 57, so here the source used is cobalt 57 in palladium. We can see that there are 6 absorption peaks, 1, 2, 3, 4, 5, 6. So this 6 peaks occurs at 5.15, 2.19, 0.67, minus 1.03, minus 3.27 and minus 5.51. So the intensities are in the ratio 3:2:1:1:2:3. So there are 3 lines corresponding to these transitions, and corresponding energies can be found by substituting the value of Gn double prime and Gn prime in the above mentioned equations. So we have considered the interaction of the nucleus with the magnetic field. So the magnetic field can be either the externally applied magnetic field, or it may arise from the interaction of the electron with the angular momentum of the nucleus. So this magnetic field, which is not externally applied but which arises from the interaction of the electrons with the angular momentum of the nucleus, is generally called the intrinsic magnetic field. So we have seen in ESR that the electron nucleus interaction consists of 2 terms. One is the dipole term and the second one is the Fermi contact term. So the Fermi contact term depends on the finite electron density at the nucleus, psi 0 square. So which give rise to an intense magnetic field at the nucleus. So the Fermi contact term is only for s orbitals, and this will give a intense magnetic field at the position of the nucleus. So this intrinsic magnetic field can cause magnetic hyperfine structure. So due to this internal magnetic field, there will be a magnetic hyperfine splitting.